Hello everyone, I'm Rishi Ranjan and today I'll be presenting the work called Adaptive Dynamic Checkpointing for Safe, Efficient, Intermittent Computing. This work was done by Kevin Maying and Brandon Lucia, who were at CMU, and the work was presented at UCINIX OSDI in the year 2018. So, before we get into the core concept of the work and the idea, let's look a little bit about what energy harvesting is about. So most of the legacy systems today and all of the computing powers run on a continued power system. This power is either supplied by the supply line or the direct AC electricity that we get at our homes or through batteries. Now, most of these systems, however, do use batteries in one form or another. As we all know that lithium-ion batteries are bad for the environment due to both their mining costs as well as their production cost and the waste that they produce. Moreover, recently, better or more cleaner energy sources have been available in the environment, which can be harvested to use for running our computational tasks. Some of these are listed beside the image, for example, wind, solar, radio waves, or even the motion energy of people can be used. The energy that is generated can be harvested to run small computing tasks. So one question that arises is what to use instead of batteries. So the industry has turned towards capacitors, which are small electrical devices that can hold charge between them. Now, the difference between capacitors and uh, batteries are that capacitors generally hold much lower energy between them as compared to batteries, as well as they hold it for a smaller duration, often discharging fairly quickly compared to batteries. However, even this small energy is a lot of times perfect for small embedded systems to run based on this harvested energies. So capacitors are charged using the energy harvested from the sources we discussed, and then this harvested energy is used by computing systems. So now focusing on what intermittent computing is actually. So intermittent computing or intermittent computation can be thought of as computation that is performed over non-continuous power and across power outages. So let us first envision how a normal continuous power computing system would perform in case of a power source like the harvested energy, where the power runs out and comes back. So if we look at the progress over time graph for a normal computing system, it would look something like the image that is shown. So the system would turn up when power comes up. It would make some progress. But once the charge on the capacitor runs out, the progress would drop to zero. However, as the capacitor charges back and power returns, the progress would again start from the zero because no state or no progress of the program was stored while it was running. And the a continuous power computing system would have to run from the beginning again. However, an intermittent computing system differs from a continuous power computing system in this way. So an intermittent computing system would start from a zero progress and it would continue and do some progress while energy is available in the capacitor. However, when the power runs out, the intermittent system must have saved some program state or some kind of a pointer to uh, to tell it when the power comes back about how much progress it had made and from what point of execution to pick up from in order to continue the progress. So the intermittent computing system would keep making progress across power cycles slowly and surely, and finally it would get to the program completion. And that is the big difference between the two different computing paradigms. Now coming on to what the different intermittent computing techniques or styles are. So the first technique of intermittent computing is called task-based intermittent computing. And this involves transforming a large program or a computing task into smaller subtasks that are to be achieved within a single power cycle, uh, basically implying progress. And once the power runs out and comes back up again, the second task can be picked up from there. And this technique is called task-based intermittent computing. The second technique is called checkpoint-based intermittent computing, and this is different from task-based intermittent computing as it keeps the as it keeps check of the program state or keeps track of the program state after a given amount of either time or energy and saves it so that when power runs out and comes back up again, we can continue the computation using the checkpoint data that was stored in the previous power cycle, and thus the progress can continue as the checkpoints are increased. Now, if we look at some of the limitations of these work, so in terms of task-based intermittent computing, so the nature of this technique requires that the programmer themselves create small tasks out of the big program that exists that intermittent computing has to achieve in every energy cycle. Now, this requires a lot of in-depth knowledge about the energy consumption of the tasks that are to be created, and it adds a huge burden on a programmer or a developer. Moreover, the the model of task-based intermittent computing ensures or demands that there cannot be any pointers or similar structures in the program due to a static memory model that task-based intermittent computing follows. Now, in checkpoint-based intermittent computing, checkpoint-based intermittent computing often adds a large overhead to the program, and it also does not have a non-termination condition imposed. Now, what non-termination means is that if there is a task or a piece of program or a piece of code in the program that is too large to complete in the between two checkpoint times, then that program would never proceed past that point of execution. So now we introduce Chinchilla, which is a compiler and runtime support for better intermittent computing. And how Chinchilla differs from other intermittent systems is what we'll see now. So first up, Chinchilla introduces an idea of dynamic checkpointing, where it says that we need not checkpoint after a fixed either even an energy level or a time duration. And this information of when to checkpoint in a program can be dynamic and changed as the progress is made. It also implements selective checkpointing in the code, where some of the checkpoints are ignored on other dynamic heuristics, which we'll look at later. Other than this, uh, Chinchilla implements a non-volatile stack in the runtime in order to reduce the amount of program stack to snapshot or restore after a power outage. It also has an undo logger to save and restore all the protected variables during the execution. We'll look at what protected variable means later. So to understand Chinchilla, it works in two different phases. So Chinchilla is implemented as a compile time transformation, where it does a bunch of compile time instrumentation and transformations to the program in order to make it intermittently executable. It also has a runtime support, which is used by this intermittently executable binary produced by Chinchilla in order to perform intermittent computation. So at compile time, the checkpoint uh, the checkpoint in the program code is inserted at block level. Now these blocks are called energy blocks in Chinchilla, and Chinchilla chooses a basic block level as the energy block level for their implementation, since they assume that basic block is the as the atomic level of checkpointing for their operations. The next the next transformation that Chinchilla employs is the identification of protected variables from the code. Now, this is done using a data flow analysis LLVM pass that is implemented. After identification of protected variables, Chinchilla implements the undo logging instrumentation to identify the writes to the protected variables between checkpoints. Finally, the memory layout of the program is transformed to place special sections or parts of the code or parts of the program into non-volatile and volatile memory. Finally, the main program of the program is also transformed in order to reinitialize state, peripherals, as well as restore from the checkpoint saved. Now let's look at what protected variables logging is. So, Chinchilla identifies two kinds of variables in a program, protected and unprotected. Now, protected variables are those whose live ranges crosses a checkpoint. So, as we have understood that Chinchilla places checkpoints at the basic block level. So there is a checkpoint at the beginning of every block and at the end of every block. Now, if a basic block is defined at one point and its reinitialization actually crosses a checkpoint between its previous definition and its next one, then its live range is set to cross a checkpoint. Now, these are identified using a backward liveness analysis compiler pass. So, these protected variables are kept track of between checkpoints using an undo log technique. So, and now we'll look at why this is important and how this is done. So, first up, this is important because consider a global variable which is stored in non-volatile memory. And let's say that at a checkpoint, all of this data regarding the program execution and state is stored. Now, if power runs out before the next checkpoint and there was a write into this global variable which is stored in the non-volatile memory, then if the power comes back and execution starts from the previous checkpoint, then the global variable value that this code between the two checkpoints would see will be inconsistent because it was already written to between the previous checkpoint. So in order to prevent this from happening, Chinchilla uses an undo log. So in this technique, what happens is that the global variable between two checkpoints, any protected variable, we'll call it, when it is written to, the Chinchilla maintains a log in the non-volatile memory called the undo log, where it stores the original value of this protected variable for its use. Now, when power runs out, then when it comes back up again, then in the main function's restoration of checkpoints, it pops all the values from the undo log and places it at the correct memory location. In order to not overly use this undo log functionality, Chinchilla also stores some metadata which keeps which stores a versioning tag for each variable and identifies that the uh, an undo log for the most latest version is used. Moreover, an added optimization is also performed for simple small tight loops. So consider this case in which I is the condition variable for the loop. Now, if I is a protected variable, then just like a loop is written, if it is I plus plus every time, then it would be stored in the undo log 100 times, which adds a lot of overhead. So instead of doing this, what Chinchilla does is that it actually creates a rare path in the program by hoisting this undo log into the rare path as well as the pre-header of the loop, so that this undo log and the rare path are only called once or at most twice during the loop execution, so as to remove this large overhead. And as we can see that the common path does not have an undo log call to it, and thus the overhead of doing an undo log 100 times is removed. Now let's understand what the non-volatile stack is. So in order to reduce the checkpointing size, which often depends on the program stack, which can grow as the program goes deep into memory, Chinchilla divides the program stack into two, which is one of which is the volatile stack and one which is the non-volatile stack. So protected local variables in the program are the ones that are stored on the non-volatile stack. And since a compiler cannot know which variables are stored on the stack and which on the heap at compile time, this is done by Chinchilla using a script after the generation of the binary. That is, the object file of the binary is actually transformed. So in order to understand the how non-volatile stack works, So let's consider this example in which the main function starts the execution, and any function with push dot any instruction with push dot nv and pop dot nv are calls to the non-volatile stack. Now, as the program executes and the non-volatile stack is filled, then at every checkpoint time, the non-volatile a checkpoint for the non-volatile stack is also saved. Now, when the program returns after power outage, this last checkpoint is the one that is the last state of the non-volatile stack in the checkpoint is the one that is restored to continue execution. So let's understand how checkpointing works in Chinchilla. So at checkpointing time, Chinchilla saves the registers and it saves the non-volatile stacks and it clears the undo log file. Now the reason the undo log file is cleared is that whatever non-committed or partially committed uh, values or writes that were in the undo log file are actually saved at the checkpoint. So whenever the checkpoint that is being saved is called, then that means that the state prior to it has been covered and the undo log file can safely be cleared. Now, if checkpoint fails, Chinchilla reverts back to the last saved checkpoint. Now, after power comes back, then Chinchilla simply empties the undo log file, restores all the registers, and restores the non-volatile stack to get to the checkpoint that was saved. Uh, a question arises is that what happens if during the restoration itself, the power runs out due to the size of the undo log, which could be large. So to deal with this, after every restoration from the undo log during the restoration procedure, Chinchilla also saves a small counter in the non-volatile memory, uh, indicating the index in the undo log to which it has actually written from. This helps Chinchilla to keep making progress in the restoration phase, as the undo log, uh, even if only one entry from the undo log is written to, Chinchilla is sure to finally get out of the restoration phase and make progress. Chinchilla implements what it calls a dynamic adaptive checkpointing. What this means is that instead of checkpointing at every basic block, which would be a very high overhead, Chinchilla uses a dynamic timer to determine checkpointing. So a simple example of how a timer works is that let's say that this is the program execution or a program code, and the five smaller blocks represented here are the checkpoint codes. Now, the green block currently is the one that has been checkpointed, after which a timer starts. Now, while the timer has still not run out, the next checkpoint code is hit, and no checkpoint is actually stored as the timer still hasn't run out. Similarly, the next one is also hit, and no checkpoint for that point is also saved to say remove the overhead. Finally, when the timer goes off, then the checkpoint that goes off that comes right after the timer is the one that is saved by Chinchilla. This removes the overhead of saving the checkpoint for every basic block. Moreover, the value of this timer is actually determined dynamically, and it is done using a binary search algorithm, where initially Chinchilla uses a very large value of the timer and then reduces it by half if the next checkpoint was never hit due to the large value of the timer. And then Chinchilla dynamically adapts this value of the interval to determine the most efficient timer interval to use for checkpointing. Now, the way Chinchilla instruments the program's main function is that if this is a normal main function shown on the left, where the program code is normally, Chinchilla simply inserts calls to two functions, one which it calls the init function and the other one which it calls the restore checkpoint function. Now, the init function is special because it allows a programmer to implement a MCU-dependent peripheral restoration or reinitialization, uh, and which Chinchilla would insert a function called to. And it also allows a programmer to do task-dependent things in the init function. The restore checkpoint is the one that restores the previously stored checkpoint and continues execution from there. Now, the final thing that Chinchilla ensures is a check for non-termination. Now, as we discussed, non-termination is a state where a program cannot uh, proceed between two checkpoints. That is, it hits one checkpoint and it gets to the other, and before getting to the other, the energy runs out, making it stuck between these two checkpointing times. Now, while Chinchilla doesn't have a compile time guarantee for non-termination, uh, it does allow checking for non-termination. Now, it implements post-compilation non-termination checking code, which users can use to determine whether there is a non-termination condition in their program or not. The way this works is that if this is the original intermittent binary with the four basic blocks represented here, and the basic block that we want to check is the green one, because checkpointing is a basic block level functionality in Chinchilla. Then Chinchilla provides a script which transforms this code into a code which only has the target basic block that we want, as well as just the initialization routine that we have. And this is the reduced binary that is used for non-termination checks. Now, for evaluation, Chinchilla is evaluated against Alpaca, which is a task-based intermittent computing system, and Ratchet, which is an automated compiler-driven system. So they're done on different open popular benchmarks like RSA, Cuckoo, activity recognition, and bit count. And they're done on different capacitor sizes and runtimes. So if we look at the runtime evaluation of Chinchilla versus Alpaca and Ratchet, and Chinchilla is used as the base metric, then Chinchilla does outperforms Ratchet by a large number while still being better than Alpaca. Chinchilla also does well on varying capacitor size evaluation, where some of the benchmarks actually did not work with Alpaca, but uh, the ones that worked on all three of them, on an average, Chinchilla outperforms both Alpaca and Ratchet. Now, Chinchilla's dynamic checkpointing solution does have a big effect on the number of checkpoints it does, as we see that the number of checkpoints that Chinchilla performs compared to Alpaca and Ratchet is orders of magnitude less. Finally, the binary size, however, for Chinchilla is much larger than both Alpaca and Ratchet, and this is down to the constant size undo log that Chinchilla implements. Thank you.